So, Assalamu alaikum to all of you. Am I audible?
Yes, sir. Assalamu alaikum.
Alaikum salam. So, last time where we left, we were discussing about the development length and the anchorage of the bars. So, we have a beam. In this beam, we have now defined we have a stirrup. We have four bars at the bottom and two bars at the top, anchor bars. Then we have stirrup. Now, the first thing is about the along the length. Is the development length of this bar going into the support. Now, this is tension reinforcement. Then there will be a slight bend here. There will be a bend here. And then the bar is projected into the support. Now, this is the development length. Similarly, for compression or anchor bars, again there is a development length. Now, let us first of all assume that for, let's take the tension reinforcement first, that this is 300 mm. From this point, from this point up till this point. And let us say from this point up till this point, it's again 300 mm. So, or let's say 250 mm. Because the overall depth of the beam is 300 mm. Then in the curvature, what happens if I extend this picture? It will be something like this. This is tension bar. It's something like this. So there is a portion of the bar which is in the curvature as well. So that means when I am saying this is 250, I am taking 250 from this point up till this point. So this is 250. I'm saying I'm taking this as 250 mm. Then from here up till somewhere here, in the tension bar, it's 300 mm. Then the rest of the portion, there will be a certain length from here up till this point, which is in the curvature. So ये portion in the curvature, it's usually 4 times phi. Phi is the dia of bar. So in curvature, you the curvature portion you usually get 4 times the dia of the bar. Now, so if we check how much is the total development length that we are providing, let that be LD. LD is development length provided. Now, how much is this? This is 300 mm plus 250 mm plus 4 times the dia of the bar. What is the dia of the bar here? We took 12 mm bar. So this overall is how much? 300, that's 550, and 550 plus 12 into 4, that's 598 mm is the development length that we are providing for this tension reinforcement bar, this bar, the blue one. So the development length is on one side at for एक support की तरफ से है. Now what is the development length that is required? Just a minute. Now the development length required as per code is from this equation. The development length is LD. So let us take this equation phi sigma s by 4 tau BD. That would be now LD required, what is required as per code, how much is the minimum? This is minimum. You can say this is minimum which is required as per code is phi is dia of bar into sigma s divided by 4 tau BD. Now, what is dia of the bar here? The longitudinal bar is 12 mm. Then sigma s, what is sigma s? It's the stress in the bar at the section considered at design load. Now, that value is usually 0.87 Fy if we take the maximum stress if it's occurring in the bar. Otherwise, the stresses could be lesser than this in because during uh, the stresses which are occurring in Anchorage, they are mostly tension stresses, but even in they could also be compression stresses. So जो उसमें stresses develop हो रहे हैं, they can even be the bearing stresses. Thereby, they could be less than 0.87. I am taking the maximum. Maximum is 0.87 Fy. Uh, now, this whole divided by 4 into tau BD. Now, what is tau BD? Tau BD, if we go to the code, it's here. The design bond stress in limit state method for plain bars in tension shall be as follows. Now, grade of concrete, we have M25 here. The design uh, bond stress tau BD is 1.4, but this is for plain bars. For deformed bars conforming to IS 1786, these values shall be increased by 60% because we are using deformed bar here, which is FE 500, not plain stress bar, which would be FE 250. So we have to increase this value by 60%. For bars in compression, the values of the bond stress for bars in tension shall be increased by 25%. Right now we are designing the tension bar, so we will not be increasing. If the bar is in compression, then you have to increase the value of bond stress further by 25%. Right now, what we have to do, because we have used M25 grade of concrete, the design bond stress would be 1.4 into 1.6 times. We are increasing that 1.6 times. So it would be 1.4 into 1.6, increasing by 60%. Thereby, this value would be, yes, कितना आ रहा है? Fy is 500. हाँ जी, anyone? 583 mm is the value of LD required. And how much have we provided? How much have I provided just now? I have provided, LD provided is 598, which is greater than LD required, which is 583. So now this is okay. The design is okay for the development length or for anchorage in tension bar. Similarly, you can design for compression bar. You can take any value uh, initially, but you have to take a greater value for compression bars. Now, how do the stresses actually occur in the supports? Now, for example, this is the support and this is the beam. Now, how do the stresses tend to occur? There is a bar. First bar is like this, then the second bar is like this. Now, half of the portion of this is going into, there will be, if this is the ends, the supports are usually in tension. So the top portion, if this is in tension here, in the support, this will come in tension. there will be reversal of stresses in the support, because there is some amount of fixity even though we are assuming this is simply supported. Now, if this is in compression, at the support at the end, this will be in compression. So there is a reversal of stresses. Thereby, now this portion, the top portion here at the support, is in tension, and this bottom portion is in compression. So while we are designing for development length, we are designing based on the nature of the bar. This is tension bar actually, but in the support this is becoming a compression bar. That's why code is taking a higher value of for the top portion, this one. Why? Because this is in tension and concrete is weak in tension. Thereby the LD to be provided, आप कहोगे कि this यहाँ कोड में mentioned है, you are taking greater value, you have to take greater value for bars in compression. The value of bond stress has to be more, 25% more than in tension. But it's actually the reverse. It's actually reverse, meaning that the bar in tension is actually in compression at the support, and the bar in compression is actually in tension at the support. That's why the code is saying that in compression you have to take 25% more, because the concrete is actually weak in tension. So don't get confused why in compression the development length has to be provided is more. So this was about the development length. Now next in Anchorage is about which we were discussing the last time is the stirrup hooks. What what does the code say about the stirrup hooks? This is the clause 26 point, this is page number 43. Stirrups, notwithstanding any of the provisions of this standard, in case of secondary reinforcement, before that there is anchoring bars in tension, deformed bars, this one, anchoring bars in tension. Deformed bars may be used without end anchorage provided development length requirement is satisfied. Hooks should normally be provided for plain bars. This is done. Now for bends and hooks. Now in stirrup you are providing the bend, the hook. The hooks, the anchorage value of a standard U-type hook shall be equal to 16 times the diameter of the bar. This is what the code says, that you have to provide a hook with a anchorage value of 16D, 16 times the diameter of the longitudinal bar. Of the stirrup. So what you have to do is hook length in stirrup. Say this is uh, H. Now this H would be this one. This is H. Let me magnify it a bit. Now, if you have a look at this, there is a slight bend first here. At this point there is a bend, then it may go straight. Now the hook in total is somewhat like this. पहले ये पोर्शन है, this one, then ये पोर्शन हुक का आता है, which is a straight portion. So there are two portions, from this point to this point and from this point up till this point in this hook. Now that total portion has to be the hook length, and how much it has to be as per code, it has to be 16 times the dia of stirrup, which is 16 times 8 mm हमने लिया है. We have provided the stirrup to be 8 mm. तो कितना बन रहा है ये? That's 128 mm. So you have to at least provide the hook length of stirrup to be 128 mm. It's in this case. So this has to be, including the bend, it has to be 128 mm. So in total, from this point up till this point, it has to be 128 mm, the hook length. Then there would be another hook, this one, and this also has to be from this point up till first till this point, and from there till this. In total, it has to be 128 mm. Clear? Everyone clear with this?
Yes, sir.
Any confusions?
No, sir.
Okay, so next we will take up. I have sent you certain questions on tutorials. One is cantilever and another is fixed support. So you have to go through them and try to solve them yourself. What we will be doing is we will be taking up the doubly reinforced sections. So next we will be working out on doubly reinforced beam sections. Now, what is a doubly reinforced section? Till now, we have studied about singly reinforced section. A doubly reinforced section is one which has got tension reinforcement at the bottom as well as compression reinforcement at the top. Before this, we were only designing the tension reinforcement and we were providing the anchorage bars at the top. Now, why is doubly reinforced section required first of all? What is the purpose of requirement of a doubly reinforced section? The first purpose of a doubly reinforced section is when you have large loads. Now, if you have large loads, that will mean there will be more and more stresses, both in compression as well as in tension. So the section, it will keep on increasing in size. So you may not be able to increase the section in size, तो हम वहां पर doubly reinforced section provide करते हैं. The second condition is जब when you have low limitations to the depth of the section. When you have limitations to the depth of the section. Now, when will there be limitations to the depth of the section? For example, there is a ceiling, and this is the ceiling. Then you have a beam below the ceiling, and you do not want the beam to be such deep that a person is standing. This is the floor at the bottom. Now, a person is standing somewhere here, and his there is less headroom here. This is headroom. You do not want this condition to happen, that the headroom is so low that it may hit a person's head here with the beam. Similarly, you want a particular headroom for movement of goods, uh, and for other things, through through these through this floor. Now, so in short, what I want to say is that this beam has got a limitation to its depth due to various things. In such conditions, you have to provide doubly reinforced sections in both these conditions, which I mentioned. One, when the load is large, and when you have the limitation to the depth of the section, of the beam section. In these conditions, what do we do in a doubly reinforced section? Now you have both compression, these are the stresses. We have already talked about this. You have a stress envelope like this for concrete in compression, then in tension. Now there will be additional compression stresses from the compression reinforcement. So you are adding up, if this is C1 of the concrete, if concrete compression is C1, this is through concrete, the forces through concrete, the compression forces in concrete. C2 will be through compression reinforcement or compression steel. These will be the forces which will be passing through the compression steel. Similarly, T will be the tension forces in tension steel. Now we have already discussed what is C1. We have already calculated C1. It was something like, can you recall, 0.326? Was it 316 or 326? Or 0.36? Just recall, into FCK into XU into B, 0.326 or 316?
247.
जी?
0.36.
0.36. And C2 is, what will be C2? It will be Fs times Fy. Sorry, it's Fs times the area of steel in compression. So what is Fs? Fs is the compression stress in compression steel. Fs is the compression stress in the compression. This is compression stress in compression steel. Then what is T? T is the, already we know that, 0.87 into Fy. So what was that? That was the tension stress in tension steel. Now, why is Fs equal to 0.87 Fy? This is 0.87 Fy into AST, into AST. T is 0.87 Fy into AST. Now for a balanced section, C1 plus C2, all the forces on the compression side will be equal to the forces on the tension side. So you can then get the equation for, this is 0.36 FCK B into XU plus Fs into ASC is equal to 0.87 Fy AST. So now for a balanced section, this is the equation for a doubly reinforced section. Now what is Fs? The compression stress in compression steel. How do you get that? And will it be equal to what you have in tension? अगर ये टेंशन स्ट्रेस के बराबर होता, then it would have been 0.87 Fy. So this is the equation here. Just, this is page number 38, and then you have page number 39. Now Fs is 0.58 Fy into area of cross section of steel required by area of cross section of steel provided. Now this one, it's based on this. Fs is the steel stress, it's based on this. Then you also have now here in this curve, if you can see, you have for a cold work deformed bar, this is the stress strain curve for the reinforcement. What you have is this is 0.87 Fy. Now for any other strain, you can correspondingly determine the amount of stress. So what do you have to do? You have to, हमें क्या करना है? We can do the reverse thing. We can first of all check what is the amount of compression strain जो हमें strain मिलेगा, corresponding to that we can calculate the stress in compression, which is Fs, from this graph. So that I will show you how it's done while we are solving the question. Now, also in the code, you will all rejoin. This session is closing.